Good afternoon, ladies and gentlemen. On behalf of the Vice Chancellor and Principal, Professor Nanapoku, it gives me great pleasure to welcome you to the inaugural lecture of Professor Werner van Zyl. Due to prior commitments, our Vice Chancellor is not able to join us, but he conveys his congratulations and best wishes to Professor van Zyl. Inaugural lectures form part of the university's public lecture series and may only be presented by newly appointed full professors who have been appointed in academic schools and centers. Inaugural lectures present an opportunity for showcasing the exciting and groundbreaking research and teaching being carried out by professors in our university. Each lecture represents a significant milestone in an academic career, providing official recognition of these people's promotion to the appointment as full professors. The lectures are also important in that they are an ideal opportunity for new professors to introduce themselves and to present an overview of their own contribution to their fields to academic peers, students, and research collaborators. It is also important that this is an opportunity for them to share this information with common folk who may not be specializing in these fields. The lectures are also a platform for celebrating a professor's academic achievement and an opportunity to do this with family and friends. Friends, mentors, and colleagues get an opportunity to see somebody who rose up the ranks in their presence and now showcasing to the whole world the achievements that they've made with their support. At this juncture, I would like to acknowledge the presence of many guests who joined us here, as well as in many other places overseas. I would like to acknowledge the presence of the members of the Executive Management Committee of the University of KwaZulu-Natal, the members of our Senate, our inaugurant, Professor van Zyl, family, friends, and other colleagues that may be joining him, academics, and all the professional and academic staff members. The students, particularly those who have been watching him as a lecturer, a supervisor, as well as a mentor. I would also like to welcome all our alumni and distinguished guests. I'm sure you're going to enjoy the lecture, but I would like to hand over to Professor Ross Robinson to produce to us Professor Werner Ewald van Zyl.
Mr. Modi, thank you for that kind introduction. Good afternoon, ladies and gentlemen. It is indeed a great pleasure for me to introduce Professor Werner van Zyl to you this afternoon. Professor van Zyl conducted his undergraduate studies together with his honors and master's degree at the Rand Afrikaans University in Johannesburg. He concluded his Master of Science degree in 1991 under the supervision of Professor Helgaard Robbenheimer, probably one of the most well-known inorganic chemists in South Africa. After a brief period in industry, Professor van Zyl continued to do a PhD. However, he did this in the United States at the Texas A&M University in the Department of Chemistry and the Laboratory for Molecular Structure and Bonding. He conducted his PhD under the supervision of Professor John Fackler, and he concluded that in 1998. In 2008, Professor van Zyl joined the University of KwaZulu-Natal as a senior lecturer, and he's progressed steadily through the ranks of the institution over that period. In 2021, this year, he was rated a C1 rated researcher, and he's been rated previously, which indicates that he's got a substantial international profile in his research. Professor van Zyl has been ranked not once, but twice as one of the top 30 ranked researchers in the institution in 2011 and in 2012. Professor van Zyl has published in excess of 100 research articles and has an H-index of 27. To date, he supervised to completion 15 PhD students and 14 master's students. Within the University of KwaZulu-Natal, Professor van Zyl has been involved in many leadership roles and certainly helped the university move forward. I'm just going to highlight a few of these, which I think really stand out. He's been a member of the school's Research and High Degrees Committee. He's been a member of many of the moderating boards. He's also acted as deputy head for the school on a number of occasions. And more recently, he was the academic leader for research for the School of Chemistry and Physics. Professor van Zyl has also been part of the organizing committee of international conferences, which I think is something that really stands out. It gives me great pleasure, colleagues, to invite Professor Werner van Zyl to present his inaugural lecture entitled Inorganic Molecules and Materials, a Career in Two Parts. Professor van Zyl, thank you.
Good afternoon, ladies and gentlemen. Thank you, DVC, Professor Albert Modi, and Dean and Head of School, Professor Ross Robinson, for the kind words of introduction. I would also like to extend a hearty welcome to friends and family, all the guests and students. The title of my talk today is Inorganic Molecules and Materials, a Career in Two Parts, which refers to molecular chemistry that I've done and also materials chemistry that I've done. It's a bit tricky sometimes to figure out exactly where to start with a lecture that summarizes many years of research. But as Professor Robinson pointed out, I started my research career at the Rand Afrikaans University, now known as the University of Johannesburg. But if you think that my grandfather gave me a chemistry kit at the age of 8, and I played with it and suddenly knew that I was going to be a chemist, then I'm going to disappoint you, because even after I matriculated, I wasn't entirely sure which direction to study. I went to the military for 2 years, and towards the end of that time, I saw a counselor that specialized in sort of career guidance, and he did an interesting test, 2 tests that he performed. The one had to do with testing my aptitude, which was more or less a modified IQ test, one could say, and the other was a general interest test. And what he discovered after that analysis was that my interests at the time and my general aptitude differ widely. And he then recommended that I study towards a science degree, because he said that natural talent won't change over time, whereas my general interest in things will change. And I think that was probably the best advice I ever received, because I've not yet proved him wrong. So I was very grateful for that intervention. So like I said, I then studied a Bachelor of Science degree at the old Rand Afrikaans University, and that went on until I exited with a master's degree in organometallic chemistry. And I performed that research under the supervision of Professor Helgaard Robenheimer. And one of the first reactions that I did had to do with a lithiated pentafluorobenzene molecule that was simply reacted with chlorogold THT. Chlorogold THT, THT stands for tetrahydrothiophene. It's probably one of the most widely used starting materials in all of gold chemistry. So keep that one in mind for the next slide as well. And then one can isolate the neutral complex pentafluoro gold THT. That was then simply reacted with the ethylene trithiocarbonate in a simple substitution reaction. And that was the first proper research result that I ever obtained. And it was part of other gold thione complexes that was already isolated by the group. And I characterized it, and that formed part of the paper. My real master's degree project, however, had to do with gold 1 and platinum 2 carbene chemistry. Carbene chemistry is a very important branch of organometallic chemistry, and one can say that at least 2 Nobel Prizes have separately been awarded based more or less solely on the functionalities of carbene complexes. In my case, what we did was we had methyl thiazole that was lithiated, and going down the path on the left, that was reacted with the chlorogold THT that I've just mentioned. That formed an 8 complex, a so-called metallate complex, meaning that there's a formal negative charge on the complex. And then that was simply either protonated or methylated with an appropriate electrophile. In this case, we use trifluoromethane sulfonic acid, which is a very strong acid, and the conjugate base of the acid doesn't behave like a nucleophile, so it doesn't interfere further with the reaction. The carbene then forms as a neutral complex. As you can see, that's usually designated by the double bond, the metal carbon double bond, indicating the carbene carbon. And one trick that's often used in determining whether a carbene carbon has formed is to look at the carbon 13 NMR spectrum, because the carbon of the carbene carbon shifts downfield dramatically, and finding its peak at around 200 to 220 ppm is not uncommon. Moving to the right side, we treated it with a platinum starting material, and it follows the same methodology. Of course, now you have a platinum 2 D8 system, so you form the square planar complexes. It also forms an 8 complex in the beginning, and then after protonation, this reaction isn't balanced, but you get the idea. You reacted with 4 molar equivalents of the acid, and you protonate each of the nitrogens, and you form the carbene complex. And since all the carbene ligands are neutral, the platinum 2+ charge remains the same, and the triflate anion balance the charge for that salt. After that, I spent 2.5 years in the industry at Implats, and during that time I considered pursuing my PhD studies. So I was looking at individuals that did gold chemistry, which I wanted to further pursue, and I eventually went to Texas A&M University, where I studied under the supervision of John Fackler. The building there that I've circled in red is the chemistry department, and I was there on the 4th floor. And my supervisor, just a bit of a academic family tree background for you, is that my PhD supervisor's office, he was diagonal across from my laboratory. Straight across from my laboratory was Albert Cotton's office, and Cotton was Fackler's supervisor, and the supervisor of Al Cotton was Jeffrey Wilkinson. And Wilkinson and Cotton has written the best-selling inorganic textbook, Advanced Inorganic Chemistry. And so in a short period of time, I had about 150 years of inorganic chemistry experience coming down on me. And so it was at that stage too late to pull up my socks. It was either swim or die. Right, what did we do? We focused on the dithiophosphanate class of ligands. That's the one I've put in a block there. And there were a number of reasons for that. The first reason was that it was comparatively rare in the literature. And so that was a good starting point. Another reason was that compared to the phosphates and phosphonates labeled A and B there to the left, those are symmetrical ligands, whereas the phosphonate is asymmetrical, and as a result, it can potentially form isomers. One drawback is that it's much harder once you start to build complexes of higher nuclearity to crystallize them because of packing problems in the crystal. For larger clusters, the phosphate still works the best. At the bottom there, I've just drawn a few contributing resonance structures, and they are relevant depending on the metal that it complexes to and the oxidation state of the particular metal. The way that these complexes or ligands are synthesized typically starts with P4S10, which is then treated with anisole, and it's simply refluxed. It's important that it's a electron-rich aromatic, because if it's not, if it's just something like benzene, then the reaction as shown here doesn't work. But as it's shown here, it works nicely, and in fact, the ligand on the left is called Lawson's reagent, and that's now commercially available as well. Then if one identifies that the anisole is an electron-rich aromatic, and so is ferrocene, and electron-rich organometallic, then you can do pretty much the same reaction. And that, in fact, did work out nicely, and one forms these dithiodiphosphatane dimers. And they are then precursors to forming dithiophosphotic acids, because all you have to do is treat it with an acid, and then you first form the treat it with a primary or secondary alcohol, and then that forms an acid. But that acid is quite acidic. It's got a pKa of about 2 to 3, and so it can be easily deprotonated and form the ammonium salt by simply bubbling something like ammonia gas through it. So I made tens of these different sort of ligands, varying the R group, making it chiral or making it sterically bulky, or whatever the case may be. Here on the left, this is cholesterol, and cholesterol has one hydroxy group right at the far end of it, and so that could behave as an alcohol functionality, and indeed that can be activated using the same methodology I've just described. And then we just made the salt of it. The counter cation is this quaternary nitrogen species, and so that worked quite nicely as well, just to give you an idea of the flexibility that can be obtained. Following the synthesis of the ligands, we then started to look at gold chemistry, which was one of the main reasons I studied with Fackler. And for someone not too familiar with gold chemistry, will probably come up with this list as to what gold can and cannot do. It's ductile, malleable, it's got high conductivity, etc. But for a chemist, the real chemistry lies in these facts about gold, which is that it has a relativistic radial contraction of the 6s and 6p orbitals. That is combined, called the relativistic and polarization effects. The strength of this orophilic interaction, orophilic from the Latin word aurum for gold, and philic meaning for the love of. Those interactions are quite strong, comparable to an average hydrogen bond of about, let's say, 10 to 15 kilojoules per mole. The orophilicity can be used as a crystal engineering design tool for increasing structural dimensionality, and that fact has been exploited quite a lot by quite a number of people. So that is one thing that's really nice about the gold chemistry, one can safely say that it's a metal that loves itself more than any other metal, because it loves to find its partner nearby and interact with it. It's got a high electron affinity, so the gold 0, so just bulk gold really, can become anion, gold minus, and then you can form things like cesium auride, which can form and be isolated, and that is actually a ionic compound, just like cesium bromide would be, and it's not an alloy. So there's no other transition metals that can easily perform that feat. Gold is the most electronegative element among all metals, and it's comparable in electronegativity to that of carbon, which means that a gold carbon bond isn't highly polarized, and so it doesn't easily causes fission between the bond, and it can be stabilized quite successfully. The value of its electrochemical potential is the lowest of any metal, which simply means that in cationic form, the gold will accept electrons from virtually all sources. And in fact, all gold complexes are really kinetic products. They are not thermodynamic products, which means that over a period of time, they will all convert back to the mother lode, so to speak, the metallic gold. Also in the solid state, or sorry, in the vapor phase, you form gold-2 dimers with a high dissociation constant, and that just reverts back to the first point I made, which has to do with the relativistic effects. Some time ago in the conversation, the academic forum, I wrote a small piece on gold as well, that you're welcome to read there. So these gold atoms, they form these interactions. Sometimes there's no interactions. If it's a bidentate ligand, sometimes you have intramolecular interactions, as the ones of the metal complexes that I'm describing. And so there's just a variety of the different interactions that can take place. The metal complexes that I was most familiar with are these dinuclear 8-membered metallocycles forming from the dithiophosphonates. In the solid state, this trans or anti isomer forms preferentially. In fact, this sign or cis has never been isolated in the solid state. And by cis, I simply mean when the two R groups are on the same side. You can see here there's an R group on opposite sides, and they are related by an inversion center right there in the middle of the molecule. So one of the things that one can start to think about with these dithiophosphonates is to do supramolecular chemistry. For example, these 9-membered gold-1 metallic triangles, they have been around for a long time. You can see already in 1970, Vaughan reported this pyridine derivative. You have these imidazole derivatives, you have pyrazole derivatives, and they all separated by a 1-2 difference in the heteroatoms. So what we asked ourselves is whether by modifying the ligand a bit and get involved with this coordination-driven self-assembly, term I think first coined by Peter Stang, whether one can kind of predict if one can't form any larger metallic triangles. And indeed, that was the case. If one starts from the trans 1,2 cyclohexanol and form the ensuing salt, and you treat it with the chlorogold THT that I've mentioned before, then you form this large hexanuclear gold complex. The reason it forms a trimer or a triangle shape, to be honest, isn't entirely clear, as it is not entirely clear for any other metallic triangle for gold or any other metal. And the reason is that in this pivot point, you got sp3 hybridization amongst the carbons. You have sp3 hybridization amongst the phosphorus on each one of the derivatives, and hence it's just impossible to say what is the natural path that will be followed. We've obtained the crystal structure of this material, and there are two types of intramolecular interactions. Intra, because it's all the same molecule. You have two types. One type is in the dimer itself. There you have intramolecular interaction of about 3 angstroms. And then you have another type of intramolecular interaction of the gold atom, and then the two situated across from the cavity. So each one is the same in that sense, and it's, other than that, perfectly symmetrical. And those are a bit longer at 3.3 angstroms. What's further interesting about this particular complex is that the way it undergoes oxidative addition across gold 1 centers. So, for example, if you treat it with a small halogen, then it goes directly from a gold 1 species to a gold 3 species. So it goes from a D10 system to a D8 system, and then gold 3 is classical square planar complex. It doesn't decompose or anything like that. It just stoichiometrically forms from there to there without any problems. And we've also managed to get a crystal structure of that product. About a year later, we wondered whether that was a once-off kind of example, or if it's a general type of example. And so I went back to the dinuclear complexes that I've made. Those aren't the only types of dinuclear complexes with the ligands I've used. You can see here I've just designated these donor atoms as an E. Now that E can be a methylene group, so a CH2 all around, or it can be a sulfur or a selenium. But what is known is that when it's a carbon-based donor, then if you do the oxidative addition, then you exclude in the right stoichiometry, then you exclusively get these gold 2 complexes. There's a formal gold-gold covalent bond that forms that shortens this distance dramatically, and then the small molecule undergoes cleavage and it binds to the gold 3. So it goes from a D10 system to a D9 system. And then typically upon further oxidative addition, it can then go from the gold 2 species to the gold 3 species. But as I've just explained, in the case of a tetrasulfur situation, it bypasses this intermediate completely, and it goes straight to the gold 3 system. And there is no real good answer yet for that reason, and why that occurs. But it occurs for both sulfur and if that is selenium. So it seems like if it's a heavier chalcogen, then it goes straight to the gold 3. What was also interesting, for the first time we could show that you can actually do the reversible reductive elimination process by treating this material with tin diiodide, and then that gets oxidized and the gold 3 species get reduced back to the gold 1, and then one can repeat that process. The other thing that we pursued was to do some of this chemistry in aqueous medium. And what was interesting here was that you can take just off the shelf copper-II chloride and treat it with this material. And then what happens is you form this copper-4 cluster, which forms immediately. But now you've reduced the copper from copper-2 to copper-1, and so something has to get oxidized, and what gets oxidized is a part of the ligand, or a remaining stoichiometry part of the ligand. So you see the reaction is 8 to 4. And then you form one cluster and then two of these. For these materials, the sulfur-sulfur coupling occurs very readily. And so you have three species, the cluster, this disulfide material, and ammonium chloride, and they are easy to separate through solvent extraction and other means. And so we were also able to get the crystal structure of this material by following this route. And it's also got very nice luminescence that I'll talk about a bit later when I talk about the materials. And one of the bonding modes you can see here is where this sulfur is biconnective to the coppers, and this one is just monoconnective. So that's always interesting with sulfur ligands, is the way that it can bind in different ways, in different bonding modes. About 10 years ago, I reacquainted correspondence with Chenhui Liu, a good friend of mine. Our PhDs overlapped. He was also a student of John Fackler, and he was just finished in 1994 when I started. And so for a long time after that, we didn't have contact. But ever since we renewed contact, he really helped me to take the cluster chemistry side to the next level. Yeri is visiting me at UKZN in 2013 when we had a Saki Inorganic conference. But basically, you have a copper salt plus the ligand plus a hydride source, typically tetraborohydride. And then you can make, depending on the stoichiometry, a variety of different clusters. These are now copper clusters. So we stay with a group 11 coinage metals. So we typically only work with copper, silver, and gold. And the idea is to see what the molecular structure of these materials look like, and then to see if anything mimics the surface of a bulk material. Because if one takes, for example, this copper-32 hydride, and you treat it further with hydride, then it reduces to the metallic copper nanoparticles. And so one tries to see a link between the molecular material and the bulk material. So let's just look closely at the copper-32H20 hydride. First of all, you can see that we had to use the symmetrical dithiophosphanate, because with the phosphonate, there's just too much difficulty in getting crystals to grow. This material exhibits a hexacap pseudo-rhombohedral core of 14 copper atoms that are sandwiched between two triangular copper. It's basically a dome, fragments of 2 by 9 copper atoms in an elongated triangular gyrobicular polyhedron. So in cluster chemistry, one moves a little bit away from the traditional geometric nomenclature of octahedral, tetrahedral, etc., just because the polyhedron won't accommodate those names as a whole. So basically, here you have the copper-14 in purple here, and then you have the two copulas of the 9 copper atoms shown here. And you can see that these are basically sandwiched between these two. And altogether, this is then called a gyrobicular because of the way that the squares and the triangles interact. So there's a whole way in which these kind of clusters are named. And so I encourage you to read the paper. There's a lot to discuss about it. The one thing maybe I can just highlight is that, first of all, this structure was determined with neutron diffraction. If you try to determine a structure like this with X-ray diffraction, you run into trouble because the X-ray diffractometer margin of error is about 1 angstrom. So even if you allocate some of the hydrogens, it's always going to be debatable how many there are and exactly what their location is. So one of the co-authors here, Xiaoping Wang, he was a PhD student of cotton, and he works at Oak Ridge Laboratory, and he was able to do the neutron diffraction study for us. One thing I should show here is, for example, if one looks at this hydride, notice that it's in a eta 5 configuration. So I'm talking about a spherical, the smallest spherical anion known in chemistry, the hydride, that is in a trigonal pyramidal geometry surrounded by 5 copper atoms. Usually it's the other way around. Usually the metal sits in the center and it's surrounded by the hydride atoms. So it pushes the boundaries for theorists to explain this kind of bonding, because we know, for example, in boron hydride, you have a hydride bridge between the 2 boron atoms, and then that is described as a 3-center 2-electron bond, because the hydride will always only have 2 electrons. So how does one explain this kind of phenomenon? So with this type of cluster chemistry, there's quite a bit of bonding features that is left unexplained. So the neutron diffraction showed this average copper hydride bond lengths. This material, I should just point out that if you have a good data set, then you can also determine the structure with X-ray crystallography, particularly if you already know where the hydrides are, and you then get quite a good data set. The problem, of course, is that referees are reluctant to accept that. And then it was also analyzed with density functional theory by Ewald in France. The other material that was recently described by us, you need this isopropyl monothiocarbonate ligand. So all we've done was we've replaced 1 sulfur for an oxygen. Otherwise, it would be a xanthate. But now it's a monothiocarbonate, and it's very rare in the literature, even now, certainly compared to xanthates and things like dithiocarbamates. And the reason is that it's a bit of a nuisance to make. I've had a student, Valny Dumini, that's successfully prepared it, because when you make the xanthates, you just react an alcohol with CS2, carbon disulfide, which is a liquid and easy to handle. Whereas in this case, you need to prepare carbonyl sulfide, which is a gas, and then that gas must react with the alcohol, and that's a bit more complicated. But going through that effort paid off, because if one just have a xanthate and you treat it with the copper starting material, you get no further than a copper 4 or maybe a copper 8 cluster. Whereas in this case, I've just drawn the 1 resonance structure, but the other one, of course, is where the negative charge sits on the sulfur, and here's a double bond, and that's what happens in this sort of super wheel. It contains 96 copper atoms, and the inner side of the ring is the sulfurs, and then there's just a dangling oxygen. So that doesn't play a part in developing this. The other thing that's interesting is it depends quite a lot on the solvent that one uses in making the material. If it's a coordinating solvent, like THF, what happens is it doesn't proceed further than copper 16, where one of the, let's say, linkages are blocked by 2 THF molecules. And then if you redissolve it in acetone, then the THF releases, and it self-assembles into this large super wheel. And so we've described that process dynamic solvation, which is just a way of saying that you can adjust an already large cluster by making it even larger through a strict self-assembly process. I mean, one doesn't have to do anything other than to just redissolve it in a different solvent. And some of this material we've sent to Professor Len Barber at Stellenbosch, and he's looking at some absorption studies for us. So we're waiting for results, because you can see there's quite large voids in the center of these, and down particular axes. You know, it might be able to absorb small molecules quite well. I want to change gears a little bit and tell you about some work we've done on nanocellulose just for the last maybe 4 years or so. Nanocellulose can be derived from many different sources, but especially plant sources, trees, etc., from tunicates and other sea material. And you can also make bacterial cellulose. So we've also made bacterial cellulose. I'll tell you about that in a minute. The nanocellulose derived from a regular string of cellulose, which contains amorphous parts and rigid, mechanically robust parts. And all you do is you hydrolyze with a strong acid, such as sulfuric acid, you hydrolyze away the amorphous parts, and what's left is the nanocrystalline cellulose. And then that is quite a useful material to further use for a variety of reactions. One of the first things we did in trying to obtain cellulose, which is different from the common way I've just explained, is from cigarette filters. Which of course can be considered as a waste, but basically all you have to do is clean it, extract it, and bleach it, and then you're left with cellulose acetate, which is basically the main component of cigarette filters, and then it just goes to a deacetylation process, which leaves you with a cellulose, and then it's followed by hydrolysis, which forms the nanocrystalline cellulose of the discarded cigarette filters. Here's a TEM photo of the fibers. You can see they extend in length no longer than about 200 nanometers, but their diameter is quite small, only about maybe 10 to 20 nanometers. So the actual ratio is quite high. And so these materials are quite useful for a variety of further chemistry to be performed. We've also been able to form the cellulose from kombucha. So in health shops, you can buy kombucha tea. At the bottom of it, you'll see something called a SCOBY, which is a symbiotic colony of bacterial yeast. One can then take that material to grow cellulose, bacterial cellulose. The SCOBY digest sugar, and it produces cellulose. So it's a biochemistry process that works quite well, and our lab has now, I think, optimized it properly. And then what one can do is, for example, add pyrrole. You can add a catalyst such as iron 3 and form polypyrrole inside the bacterial cellulose. And what's interesting with this is that it's done dialysis free, because one of the big things that waste quite a bit of time when you go through the normal acid hydrolysis step is the dialysis step that follows right at the end. and that can take up to a week to remove all the strong acid component from the surface. In this case, that's not necessary. It's directly precipitated together with the polymer, and then using PVA, one can form films that now is conducting because of the polypyrrole, which is a conducting polymer. And so, and because of the nanocrystalline cellulose, it is mechanically very robust. So this is a way in which interesting new materials can be made and formed. Another thing that we've done was to use the cellulose, dissolve it in a solvent called Schweizer's reagent, which is really a CopperII complex. And the reason why it dissolves, because it's quite tricky to dissolve cellulose, you can't dissolve it with an organic solvent, is it breaks up all the intermolecular interactions between the cellulose strands, and it forms these CopperII complexes. And the way then that you release the cellulose back into solution is by simply treating it with an acid. Well, we know from the previous work I showed you earlier that if you just take the dithiophosphonatic acid and you treat it with a CopperII chloride, you form this cluster. And so we thought maybe that same process can work here. So we had the Schweizer reagent complexing with the surface of the cellulose, and then we simply treated that with a dithiophosphonatic acid, and we were pleasantly surprised that the copper 4 cluster formed, sorry, the tetranuclear cluster formed, and because it luminescence, it caused the entire film that was now formed to also luminesce, as you can see here. And we could, through a separate procedure, show that it is definitely the same tetranuclear cluster that we originally isolated, that now formed again. And yeah, you can see the editor was kind enough to allow us to be on the front cover of this particular issue. It's a relatively new journal, about 2 years now. And so this work was done by Stephanie Fraser as part of a master's thesis, actually. So that is what I wanted to tell you. I hope that I could show a bit of a bird's eye view as to the carbene chemistry that I started with, then moving on to the dithioligands, the gold complexes that was made, moving on to the copper hydride clusters that was made, and then eventually using some of those tools to go into the material side of things. I would like to acknowledge mentors that has assisted me along the way, starting with Helga Drobenheimer during my master's degree, John Fackler and Al Cotton during numerous joint group meetings that I've had together, and was able to tap into their expertise. After that, I did a postdoc in the Netherlands. I didn't talk about that, but that laid the foundation for doing work in material science, because the big difference is that the tools that one uses in that regard is much different than the tools one used to characterize molecular compounds. So my mentors there was Henk Verwey. For the first 2 years, he migrated to Ohio State University, and then he was later replaced by Dave Blanc. And then at the start of my career at UJ, I was thankful for James Darkwa, who also pointed me in the right direction on many occasions. A number of students that I've graduated to completion, that I'm very thankful for. Without them, none of this work could be possible. I've only highlighted some of the work that many of them have done. The group is unfortunately getting smaller and smaller, it looks to me. I think it's to do with the COVID situation. So hopefully next year we can start to reboot again and start new types of chemistry with a larger group. Collaborators, that was very useful along the way. I've talked about Chen Wei Liu, dear friend of mine, and then Derek Willens, with whom I've wrote an extensive review in coordination chemistry reviews, and he's also very helpful. Narish Prasadu, that's at the University of Zululand, that I've only started to collaborate with in the last 2 years or so, when one of my PhDs actually moved to him to do a postdoc. So we found a way to make phosphides by decomposing the dithiophosphonates. Prof. Jono Lagada is Jono Lagada, with whom I've also published a number of papers. I was on sabbatical in 2014, where I worked with Ronaldo Poli in Toulouse at the coordination center there. He was in fact also a postdoc with Al Cotton, but I didn't do much catalysis there. That was where the idea of nanocellulose first germed. James Wilton Eli, spent 2 months with him as well at Imperial College. This was at a day that we spent at Lord's cricket field, when I still had more respect for the South African cricket situation. Alan Hutton, I didn't talk about work that is imminent. I visited him at MIT. He's actually South African, and he got his undergraduate engineering degree at Howard College, just minutes from where I'm sitting now. But he pioneered a capacitive deionization process for water desalination, which is one of the things that we would like to look into in the near future. Colleagues on the Westville side, in particular, inorganic chemistry that I interact quite regularly, Mohammed Bala, Vincent Niamori, Bernard de Waga, Olga Friedrich, Ord Munro, he's since left for WITS, BJ Martinshi, Zamu Shozi, Subu Singh, and our crystallographer, Sizwe Zamisa. And last but not least, my family, wife Joanne and daughters Kelly and Amy. Not always sure how they keep up with me. And then thanks to the funders, that is gratefully acknowledged. And thank you.
Professor van Zyl, congratulations. Well done. It was a wonderful presentation, very relevant across many fields. We really appreciate particularly the fact that you're showing us as a university the importance of collaborations and the acknowledgement of the people who are funding our research. I still see many great prospects and opportunities into the future. I hope you are going to stick around at UKZN and attract more students from all over the world and assist this university to reach its potential to be an inspiring university, a university of greatness. We really thank the people who assisted you to be where you are today. I have to overemphasize the university's special thanks to your wife and children. Well done. Colleagues, ladies and gentlemen, thank you very much for joining this wonderful talk. Please join us again as we continue with these exciting lectures that are coming from our super professors. Thank you very much.
Thank you.